300 meters below the surface of the North Atlantic, the ocean presses inward from every direction at once. Not from above. Not from the sides. From everywhere, simultaneously, with a force of roughly 30 atmospheres, 30 times the weight of the air column above sea level, bearing down on every square centimeter of metal in contact with the water. A nuclear submarine moving at depth is not gliding through an empty dark. It is threading through a medium that is actively, constantly, mechanically trying to crush it into a ball. The hull is not passive in that equation. It is fighting back, every second, through nothing more than geometry and the molecular stubbornness of specially made steel. And the fact that it succeeds, that it has succeeded, reliably, for decades, is one of the quietest engineering achievements in human history. Here is the puzzle. Steel is strong in tension. Pull it apart and it resists magnificently. But compress it from all sides at once, and a different, darker physics takes over. At sufficient pressure, steel does not bend gradually. It does not warn you. It buckles, suddenly, catastrophically, in a fraction of a second. Every naval architect who has ever drawn a submarine hull knows a number called the collapse depth, and that number is not a comfortable margin above where the vessel normally operates. The margins are calculated, they are real, but the mechanism of failure, when it comes, is essentially instantaneous. So why does a submarine hull not do exactly that? Why does the geometry of a cylinder, pressed from outside, behave so differently from what common sense predicts? And why is a scratch, a dent, or an improperly welded seam not merely a maintenance problem but a potential death sentence for everyone aboard? By the end of this, you will understand the actual trick. And you will be able to explain it to someone else in about 30 seconds. Begin with pressure, because pressure is where the logic starts. Water is roughly 800 times denser than air. That density means that every 10 meters of depth adds approximately 1 additional atmosphere of pressure, roughly 14.7 pounds per square inch, or about 100 kilopascals, for every 10 meters you descend. This is not approximate in the casual sense. It is a reliable, linear relationship derived from the weight of the water column above you. At 100 meters, you are dealing with roughly 11 atmospheres total, 10 from the water, 1 from the atmosphere above the surface. At 300 meters, that figure is closer to 31 atmospheres. At 600 meters, 61 atmospheres. A U.S. Navy Los Angeles-class submarine has an official test depth of roughly 290 meters and an estimated collapse depth that naval architects place at somewhere above 730 meters, though the exact figure remains classified. What matters for our purposes is that the gap between those two numbers is not comfortable padding. It is engineered geometry, expressed in steel. Now consider the shape. A flat plate pressed from one side bends. Press it from both sides simultaneously and you have a different problem. You are loading it in pure compression, and flat plates under pure compression buckle unpredictably. But curve that plate into a cylinder, and something changes fundamentally. A cylinder under uniform external pressure converts that pressure, which would ordinarily push the wall inward, into a stress that runs along the circumference of the cylinder. Engineers call this hoop stress, and in a tube under external pressure it tries to compress the circumference, to shrink the circle. The cylinder, if it is a perfect circle, distributes that compressive force evenly around its entire perimeter. No single point is being singled out. The load is shared equally by every molecule of steel around the ring. Think of it like a Roman arch. The stone at the top is not being crushed downward by the stones above it, it is being squeezed inward from both sides, and that inward squeeze is what gives the arch its load-bearing strength. The submarine hull is that arch, bent all the way around into a closed loop. This is the trick: a perfect cylinder, uniformly loaded from outside, turns external crushing pressure into circumferential compression that the whole structure shares equally. It is geometry doing the work, not just material strength. But geometry alone is not enough, because the ocean is not a gentle loader. This is where the steel specification becomes critical. The United States Navy developed a steel grade called HY-80 in the 1950s. The HY stands for high yield, with a yield strength of roughly 80,000 pounds per square inch, or about 550 megapascals. Its successor, HY-100, reaches approximately 690 megapascals. These are not simply stronger versions of structural steel. They are alloys designed to absorb energy without becoming brittle, which matters because brittle steel does not deform before it fails. It shatters. HY-80 and HY-100 were engineered to remain ductile, to bend rather than snap, even at low temperatures and under impact. Every plate is tested. Every weld is inspected by ultrasound and X-ray. A weld defect in a pressure hull is not a cosmetic imperfection. It is a local disruption of that perfect load-sharing geometry, a point where the hoop stress concentrates instead of distributing, and that concentration is exactly where a buckle will initiate. Which of these would you least want to stand next to, a submarine at test depth, a naval gun firing at maximum charge, or a structural column in a building at its rated load limit? Leave your answer below. Here is the false belief that most people carry into this subject. People assume the danger at depth is straightforward: more pressure, more uniform squeezing, and eventually the steel simply is not strong enough. That picture implies that failure would be gradual, that walls would slowly deform inward, giving time, giving warning. The actual mechanism is nearly the opposite. The failure mode engineers most fear is not slow plastic deformation. It is what they call elastic buckling, a sudden geometric instability in which the hull, which has been holding its circular shape under compression, abruptly and irreversibly snaps into a different shape. It does not melt. It does not slowly cave. It pops, in a fraction of a second, into an oval or a series of lobes, and that geometric change releases the stored elastic energy all at once. The implosion of a submarine hull is not a crushing. It is more like the inward detonation of a structure that has been holding a coiled tension, waiting for one imperfection to give it permission to release. The crew would have no awareness of it. The event is measured in milliseconds. This is why submarine engineers obsess over roundness. The rounder the hull cross-section, the more perfectly it distributes hoop stress. A deviation of even a few millimeters from true circular can create a stress concentration that drops the effective collapse depth dramatically. The internal ring frames, the circular ribs that run around the inside of the pressure hull every half meter or so, are not there primarily to add material strength. They are there to maintain the geometry, to enforce the circle and prevent the gradual ovalization that would otherwise occur under sustained external pressure. They are the enforcers of the shape that makes the physics work. Modern submarines add one further refinement. The outer hull, the hydrodynamic envelope that gives the vessel its smooth, whale-like profile, is not the pressure boundary at all. It is a fairing, a skin that manages water flow and reduces acoustic signature. The actual pressure hull sits inside it, shorter and fatter, a cylinder of HY-100 steel. The space between the two hulls is flooded with water during a dive. The outer envelope never has to resist pressure because the pressure is the same on both its sides. Only the inner cylinder is keeping the ocean out, and it does so entirely through the alliance of steel grade, ring frames, and geometry so precise that fabrication tolerances are measured in fractions of a millimeter. At 300 meters down, every square meter of that inner hull is absorbing the equivalent of roughly 300 metric tons of force. The entire pressure hull of a Virginia-class submarine, roughly 33 meters long and 10 meters in diameter, is absorbing a total external load that staggers arithmetic. And it does so continuously, silently, without so much as a creak audible to the crew inside, because the geometry is doing its work perfectly. The moment the geometry is no longer perfect, a buckle, a weld crack, an impact dent, that arithmetic does not ease gradually. It resolves instantly. There is a certain awe in the fact that human beings have chosen to inhabit this environment at all, and a different kind of awe in the engineering that makes it possible. A cylinder of carefully alloyed steel, machined to near-perfect roundness, stiffened by precisely spaced rings, welded to tolerances that would embarrass a Swiss watchmaker, that is the entirety of what stands between a crew of over 100 people and 300 metric tons of water pressure per square meter. Not electronics. Not computers. Not active systems. Geometry and metallurgy. A shape holding a force, the way an arch has held a force for 2,000 years. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.